Hello everyone, my name is Gabe and welcome to my channel. Hope you guys are enjoying your day. In this video, I wanted to show you really quickly how to model these guys. So the figures that look like this, okay? Now, what they mean to me, I'll explain really quickly. As I was writing my undergraduate thesis in physics entitled Investigating Induced Electric Dipole-Dipole Effects on Anderson Localization of Ultrasound and Dielectric Mesoglass, I was investigating the Anderson localization effect using ultrasound and using borosilicate beads, which are lightly sintered to form a slab. The slab will go into a water tank, and then we'll send ultrasonic signal from one side of the slab and use a hydrophone on the other side to observe the signal and analyze it, etc. It's a lot more deeper than that, but for the purpose of this video, that's what happened. So in essence, when you observe the signal, depending on a lot of things, but in general, the frequency and the arrangement of the atoms, or the amount of disorder, and by atoms I mean the beads, you might observe two types of regimes, or two regimes. Obviously it's a spectrum, but the one type is the diffuse regime, which you can see on the left, which I used a Gaussian to model here. So this is just a normal distribution, obviously not in 2D, and it has a standard deviation centered about a 0 of the 2D plane upon which it sits. And on the right hand side you will see the localized regime, in which energy is localized. It's no longer diffusive. So yeah, I could go on and on about the actual research, but let's get into the code. Let's do it. Okay, so the function is called diff_v_loc with one input, dim, which stands for the dimension, and obviously diff_v_loc is diffuse versus localized. And the user input dim here simply establishes the dimension of the scale of the figure. Okay, we will see how this input will affect the resultant figure later. Okay. So we jump into here. Okay, we establish the xy plane. Xs and ys are the same, because you set xs equal to something and then ys equal to xs. So what they will be essentially are 1 by 2 times dim plus 1 matrices, which range from minus dim to dim. Okay, the plus 1 comes from the inclusivity of 0 as you cross over from negative to positive values. Let's say, for example, your dim value is 2. You will go from minus 2 to minus 1 to 0, 1, and 2, which are in total 5 values. So that's where the plus 1 comes from. Next, we'll use the mesh grid function, which will basically take our xs and ys matrices and we'll turn them into a mesh, a 2D mesh of coordinates based on the coordinates contained in the vectors xs and ys. I won't go into too much detail about this function, which has a lot of utility, and I think we use it twice here. But I will, however, link a video from another channel in the description, as this other channel does an amazing job at explaining the intuitive idea behind the function. So next we establish a sigma value, which will serve as a standard deviation for our Gaussian function, which we will call, or which we will use in a few more lines, which is only used in the diffuse case. Okay, this value will of course dictate how wide or spread out the base of the figure will be. If I could show you perhaps. No. Yeah, so it'll dictate how wide the purple center will be, how much of the 2D plane it will cover, this sigma value here, okay? So back to here. Okay. Next, We then set an adjustable normalization constant, which to simply contract the height of the peak relative to the overall scale of the figure. Okay, so this is just, again, an adjustable normalization constant. When you use the code, you're free to adjust it as much as you want. I would just start by adjusting this constant here and see what type of results you get. Okay, and then for the final step in the diffusive case, you will get the z-vals or z-values from taking the norm, this normalization constant, and multiplying it by this Gaussian, okay, which it takes in our x and y values at each point of the mesh, which we got from the operation up here, the mesh grid operation up here. It'll take each one and it will output values which go as or follow a Gaussian distribution with a standard deviation, as we said above, okay, which is here. Yeah, that's it for the diffuse case, okay? Okay, so as you can see, I am indeed wearing a new shirt, and it is light outside, and that's because last night it was getting a little too late, and I couldn't finish up in time. In any case, I'll be doing that now. So, yes, to now the figure which I consider the more challenging out of the two to code is this one right here, which in the context of my research demonstrates the regime in which the disorder of the atoms which make up the medium through which these ultrasonic waves propagate will result in the localization of this energy due to wave scattering and interference effects within the medium. Now, in actually a 2008 paper published by the group from my, which I guess at the time were working in the lab, which I'm currently working at, have shown to successfully localize ultrasonic energy in aluminum, in an aluminum sample of these beads. Okay, whereas I am working with a dielectric material, these borosilicate beads, which have these, long-range induced electric dipole-dipole interactions, which may or may not inhibit the localization of energy. In any case, so back to the code. Okay, we use the same dimension scale as we established before for the diffuse model. However, this time we take a different approach. Now, I was messing around with this for a little while, for a little bit longer than I'd like to admit. But eventually I figured out that the easiest way was just to construct a bunch of circles like these, right? Each of which has a different radius. Starting from the center, it increases in radius in even increments, right? And the whole idea was to just take these flat circles on a 2D plane, pull them out to have a cone in essence, and then just modulate the radius or the curvature of the cone to no longer go as a linear function, but rather as an exponential one. And then you get this curve shape. And that way you don't have this error of having a hole in the middle if you're using a 1 over x function, okay? And also a 1 over x, at least in my case, has been annoying to deal with because it was just the curve was actually too sharp, and it would just, it would give me a lot of issues. It would go frame a lot, and I'd have to deal with the scale. In any case, this is the most optimal way that I've found to go about this, okay? In any case, so as I said, we will construct a 2D set of circles where the circle with the largest one holds inside of it the circle with the second largest radius, and so on. Okay, so then let's get right into it. We jump into these scales here. So here we have a z scale of how high the peak will be, a b scale of how wide the base will be, and again, these I have worked. I spent a lot of time perfecting them, so as it sits right now, the scale is, the figures are relatively even. So if you are to show both of them at the same time, like they are in scale within each other, okay? So they're like appropriate to show in like a side-by-side type of fashion, okay? But again, if you just need one of them, you can adjust either scale to your liking. So in this step here, we get the radius values. We have 0 to b scaled times 2 times pi in dim amount of increments. Theta from 0 to 2 pi. Here it's the same thing except for the b scale. And then we use the mesh grid again with inputs r theta to get a 2D mesh of r and t's. And then using polar coordinates, we extract the x and y coordinates using r sine theta, r cos theta, and again, due to the symmetrical nature of this shape, you can use r cos theta equals y, it doesn't matter, r sine theta equals x, but in any case. So up to here, it's, everything's fine and dandy, but what we achieve if we were to just plot it now, so essentially what we're plotting as our z's, as our values for z is just the radii, right? Now we want these radii to first of all open downwards, so the concavity is this way, which I believe is concave. Convex is like this. In any case, I might be wrong. So as of this point, we have our r's opening upwards as just a cone, okay? And in this step here, we flip them. We flip the cone. We add an offset, right? Because if you flip it right away, it's just going to be under the 2D plane. So we flip it. We add an offset. It's out of the 2D plane. And then we add a z-scale to, this is just another scale factor of how high it'll be. So it's either here or here. I added them in both places. It works perfectly for me. This might be completely, useless, but in any case, it works for me. Okay, and then we use this exponential function, which it takes 10% of the z values from here, because I found, again, this is a perfect, balance, okay, between the height, between the width of the base of the figure, the 2D plane, and the relative other diffuse model. And again, it's all adjustable to however you like. Yes, so it's as easy as that. You take the exponential of the z's times 10% of them times 0.1. You can mess around with this if you'd like, and then after this point, this is just a bunch of plotting sequences. You can also mess around with this. You can add your axes. You can add some color. You can use a different color scheme if you'd like, but I chose this one, which I thought was cool. Oops. Yeah, so if you enjoyed the video, please leave a like. If you learned something new, also leave a like. If you have any comments, any questions or concerns, or even advice, I do like to improve, please leave a comment. And if you'd like to see more content like this or other content, which I'll be posting, I'm not exactly sure what other content I'll be posting, hit the subscribe button. And yeah, other than that, I hope you enjoyed the video and have a good day. See you.